All right, so shall we get started then? Okay. Well, first of all, I didn't realize you were waiting for me, but thank you for doing that. I just came out of a PhD defense in Packard. So thank you everyone for being here. I'm not going to introduce Jim. That's Shrabanti's job, Professor Chaudhry's job, but I wanted to introduce the series. This is a new series that we're starting in electrical engineering called Meet the Faculty. This has been discussed by the Culture, Equity, and Inclusion Committee for a while, with encouragement from our department chair, Professor Jelena Vukovic. This is the first event. So here, we're breaking new ground. Thank you for being here in person. I see about 25 people here. Is that what Mary Kay said? About 25? No, here in person. About 25 here. So the room, those of you who can't see the room, it's about a third full, maybe a little more than that. And 30 on Zoom. Mary Kay just updated us. So that's pretty good, pretty good. Anyway, this is, breaking new ground. So I just wanted to mention, what is happening to introduce the series. I think that's it from me, really. I'm going to hand the microphone off to Professor Chaudhry, who's going to introduce our main speaker.
Thanks, Eric. Well, welcome everyone. And this is, as Eric just pointed out, this is an exciting series where Jim is breaking the ground or ceiling, I don't know which one, but we are very excited to have Professor Jim Harris, and I would probably keep everyone with their first name at the very start of it. So it's a privilege and an honor to introduce Professor Jim Harris. Jim. Well, to those who know compound semiconductor, for us, Jim has been an institution. That's probably the best way of introducing him. As an MBE pioneer, as someone who pushed the limits of 3.5s, the conventional 3.5s, like gallium arsenides and stuff like that, which is today in application, Jim's role is one of those of a pioneer. So that's more of the knowns of Jim. We can call him a lifer at Stanford, who earned all his degrees, the bachelor's, his master's, and his PhD from Stanford Electrical Engineering. So who could be a better person to get this series started? So those are the knowns, okay? So we can look it up even on his website. What we are here for is to know about the unknowns of Jim. So for that, I would just add a couple of pointers here. One of that, he's the coach. So to all his students, he's the coach, and a coach is best known by the team members once they have left him. So we see a lot of his students back here. I mean, some of Jim's students are here in the audience. That speaks volume about what kind of a coach he was. And I'm sure they have a lot of fond memory to share about Jim. I would add with a shout out, I would also add a shout out to Joyce Harris, who is here. Jim and Joyce met 65 years back. Guess where? At Stanford on campus. So we have Joyce with us. And he actually, and I spoke with Joyce just to make sure all the things that we talk about Jim are validated. So Joyce gave me a certification saying that he is indeed a good guy. So no problem on that. She said something about Jim, which I want to just quote. He's optimistic, energetic, adventuresome, determined, and fun to be with. So I think no one can define better than Joyce can. So thank you so much. And also one interesting thing about Jim's philosophy of teaching and research. How did he succeed so much? So, well, the way he did it is get good students and get out of their way. So with that, I would just hand it over to Jim to share all the unknowns that we want to know. And we have a lot of questions already at the end of his brief introduction. This is more of an interactive series, so please feel free to ask any question from Jim directly. Thank you so much, Jim.
So I think I'm hooked up here. Okay, thank you very much, Shrabanti, for the introduction. And it's certainly an honor to be the first speaker for this, and especially to see Professor Jim Gibbons in the audience, who I will mention a little bit later. But Some years back, I made a list of 10 people that truly did change my life. That, you know, something I learned from them, it changed the direction that I chose. And Jim was one of those people. And so it's truly an honor that he's come to see me again. Let me first start with hopefully some things that will be, maybe you kind of wonder, why am I even listening to this? But hopefully, first of all, you're a group of really intelligent, smart, ambitious young people. And you're going to accomplish a lot of things in the world. And so the last number of years, I've hopefully planted some seeds that you'll think about, and you may not recognize, you know, where you kind of got this 20 years from now, but it strikes a bell, and I can certainly relate that in my own personal experience, that some things that, you know, happened and it just kind of went over my head, but some years later, I said, whoa, that was something I should have paid a little more attention to. So this is something I put practically in every class that I taught. This as a quote from Louis Pasteur, that in the fields of observation, chance favors only the prepared mind. And so I can tell you, I don't know, many tens of quote accidents happened that I suddenly thought it wasn't really an accident. It wasn't something I had planned, but it's been an experiment sometimes that didn't turn out the way I thought. But instead of feeling it as a failure, to kind of look at it and say, whoa, maybe that's something I should look at further. In some of those cases, it's turned out to be way more profitable than the way I was headed. So, oops, I had the wrong direction here. So I've tried to distill some of the thoughts I had on both successes, which when I was at your stage, that's practically all I was thinking about. But I can tell you, as now being retired, and some of my colleagues that have retired just find there's a vacuum. And I would say, if you find something that you have a real passion for, and particularly that both professionally and recreationally, something that really, I always say, makes your heart sing, something that you love to do. And among those things, Olaf always, he's always deriding me about my skiing because I beat him in a ski race. Oops. Oh, how did that get clear? Yeah. All right. Yeah. Just remember that ski race. Where's my mouse here? Here we go. Okay. I have to tell you, it's been 2 years almost to the day since I was doing any teaching or anything. And it took me a while to figure out how to get PowerPoint to work. Okay, thoughts on success. So, as I say, find something that you really love to do. And so I've always cycled. I used to run, but skied. I learned that from my wife. Anyway, I'm going skiing for 3 weeks in another week, and so it's something I still really love to do, and I do with my sons and my granddaughters. And certainly try to develop a vision and see the big picture. Just don't get always focused on what you're doing, but see how it fits into the system, and you can contribute, and often just pick out a particular part of a big problem in which you really have something specific that you uniquely have. Be a good observer. many important, as Pasteur said, many important discoveries were, quote, completely unexpected accidents. Learn from your failures, both your own and some people, and I've certainly seen this, you just say, how could I have failed? You just kind of, it's a setback. But people that are really successful really learn how to learn from that. And often it could have almost been more in the category of an accident that you say, whoa, all right, I failed at what I was trying to do, but I see some new insight that enables me to do something even better than what I thought. And look for opportunities where your particular skills are unique and you can go off the beaten path. I've had numerous cases of that. And don't be afraid to take risks. Sometimes it didn't turn out quite right, but I always like this. If you're on the frontier, there's no guiding stars. You look up in the sky and just think of Columbus headed across the Atlantic and thinking, man, where's the North Star? Oh, I think I see that maybe that's the North Star, but what are all the others? So you have to find the route. And the beauty of that is if you find a new map, you can provide it for others to follow. So few more is stay healthy. You don't always have a choice about that. Some people get cancer and things, but over the years, I found that people that got stuck in traps with drugs and things, it just creates a depressed and less creative mind. And I've played sports and things all my life, and I cycled 6,000 miles this last year, and so just do your best to stay healthy. It makes the mind work better. Perseverance is just, many people drop out of the competition when the going gets tough. But if you're really determined, you'll hang in there. And teamwork is, particularly today, 50 years ago, people could make individual contributions much more so. But today, the world and science is so interwoven that it's really largely a team effort. And keep learning and trying new things. I still try to do that my own, and it keeps your life exciting. And participate actively. And it may be some number of years before you really do this, but the past year I've participated in 14 demonstrations. One of the things I remember is I thought Stanford should be leading the way in the Board of Trustees divesting from all fossil fuels. And after so I went with the students. I was one of 2 faculty members that went with the students and delivered the petition that, quite 500 or so students had signed and delivered it to the president's office. And so I've continued to battle with the board saying they should, but they did fairly soon divest from coal, but they still are debating about what to do with fossil fuels. But to me, for 20 years or more, the environment has been under severe duress. And I have to say I'm part of the generation that did create that problem. And your generation is going to have to solve it because it's getting worse. So actively participate in the causes in which you believe in. And finally, just as I mentioned with Jim Gibbons, that I had the opportunity for these 10 people to really thank and tell half of them how much their impact had been. The others had passed away. And I didn't learn that till I was quite a bit older, but it does, and I've certainly experienced that more recently. And do whatever you do with enthusiasm. So, and a favorite saying of mine was, do it, whatever you do, with enthusiasm, and do it hard. And so these next couple of, this was from my retirement party. And so this was, I could say, sort of my guiding star. This was my advice to all my students. And this was my students' advice to me. It says, crossed out with hard and less and more. Why does it not want to move? Okay. So this is kind of my life story in a slide here. This happens to be the very first point contact transistor, and I had the good fortune to have this passed on to me by Gerald Pearson, who was Walter Bratton's office mate at Bell Labs, and he signed Walter's lab book on Christmas Eve night, the day they got this first point contact transistor to work. And so when Gerald was leaving, he said, you know, this means nothing to my children, but he said it would mean something to you, which it certainly did at the time and has. There's Noyce's first and Fairchild's first integrated circuit with 4 transistors. And this is a modern microprocessor, you know, now with 1 billion transistors. So could anybody have ever thought this was possible? For sure not. So one of the things I like to say is certainly miniaturization and integration. You know, could you imagine trying to put 1 billion of these things into any? It would have taken this volume of this entire building. And so, having worked on gallium arsenide all my life, I always say, you know, silicon is incredible, and we've made it even though the semiconductor fundamentally is just mediocre in terms of transport and recombination and things. But what it does have that no other semiconductor does is silicon dioxide. And that has been the real enabler, being able to isolate things and put interconnects and everything. And today, my colleagues, Srabandi and Eric, are, you know, at the forefront of working on new materials and devices. And so new materials are really key to that. And I would say one of my former students, Professor Daryl Shlom at Cornell, using MBE, discovered the right combination of metal oxides and their stability on silicon. And so hafnium oxide that he demonstrated first is on all of today's, the ultra thin oxides on all of the silicon ICs. So this is just, you know, Moore's Law. I've been listening to I just finished Gordon Moore's book, Moore's Law. And it's just having lived through all that. And of course, Jim Gibbons even worked before that with Shockley. And so Moore and Noyce all worked for Shockley also. He had an incredible talent for picking brilliant people, one of them sitting there in the back of the room, and leading the way to new things. But so you need to think, what could I possibly do with 10 to the 12, not just 10 to the 9, 10 to the 12 devices on a single chip, because I'm almost certain it will happen. So just dream big. And I like this of Thomas Edison that speaks of perseverance and don't give up. And so the final slide is, I like this one, the frog not wanting to be swallowed up out in the marshland, and that the incredible revolution that you're kind of inheriting, but Jim and I had the incredibly good fortune to be both in time and in place at Stanford, where it was the heart of this world. And so we've had a great career in being part of that. And so for you, the challenges, I believe, is going to be in the environment. And can we really change the energy production and consumption for the it's more kindly to the environment? So thank you, and I'll take any questions people have. So were you going to do the ones that people had sent in first, or okay? All right, great.
Already, already collected, and thanks to Mary Kay, she is, I can't see her right now, but she helped us with this question. So Jim, shall we get started with the, so before all of that, let me tell one part of your story that you didn't discuss, which is you being a member of the Leland Stanford marching band.
Oh,
I wanted to bring that up.
yes.
During your introduction, so member of the, what is it called? The Leland Junior Stanford University marching band, right?
Yeah, I always remember when I went to USC. It was the first airplane trip I had, was when the band went to play down in the Coliseum at Los Angeles. And one kid, when we were going in, says, "Is Stanford only a junior university?" But I have to say, at that time, Stanford was really best known where wealthy people sent their kids to college. It was about the time Jim Gibbons started here. Maybe he was the one that caused it. No, I believe it was really Fred Terman and Wallace Sterling. But they decided it was Stanford was going to change, and they made it happen. Oh, yeah. Oh, I'd always played a musical instrument, and so it was actually a pretty wild, crazy outfit in those days. I mean, the kind of things we did, they'd throw us out of school today.
Okay, on that happy. I would take the silence for the answer. So let's get started with the question. So the first question we have from a graduate student: how has Stanford changed over the years you have been here? What directions would you like to see us take in the future? Do you think we are heading in the right direction?
Okay, well, so first, how has it changed? Woo. Yeah, well, you could imagine from the band episodes, we just got scolded a few times. But anyway, I guess first and foremost, when I came as a freshman in 1960, it was 75% men and 25% women. And so virtually all of the people we know were the man and wife are Stanford graduates. The men are always 1 or 2 years older, because the picking was pretty slender when you finally figured this out when you were a freshman. So I met my wife about the 5th day she was on campus. I came back to school a week early so I could try to find a date. And we met on a blind date. And it worked out 60 years later. So that was one thing. Second was Silicon Valley didn't exist. In fact, there were still a couple of fruit orchards and things and fruit stands and things along El Camino between here and sort of the really nearest kind of big shopping center was down on San Antonio Road. And so if you drove down there, there was still sort of fruit stands and things. And so there were virtually no students. There was one student that I knew that was in my class that was from, I believe, from Nigeria. But I mean, there were literally very few Asian students or students of color. But that started to change just during the time while I was, let's say, as a graduate student. So in that period of the late 60s, it did change. Are we headed in the right direction? I would say sort of. I still think particularly the Board of Trustees is too conservative. It's still kind of dominated by pretty wealthy white men. They're doing a little change of that. I'll tell you a little bit later what I've been up to a lot, but I sort of believe it's never going to change unless old white men make the move to start to make it happen. And that I think they need to listen to the young people. And I would just say it's okay to have people with more experience like me. I'm almost 80, but I do listen to young people still. And I think my experience is just so much with young people. And you know, they're the ones that really are at the forefront and have new ideas and new ways of thinking. So I would say, you know, really don't be timid about, you know, things that, if you've got an idea, talk to people and you know, it may take a while to nucleate and get things to move forward, but I sort of think the Board of Trustees, you know, they're creating this new school of sustainability, which I think is good. I just wish they would be a little more activist and do it. You know, if they would just listen to me and do it right. I just think that they're still kind of on the conservative side, and so they're just slowly moving in the right direction. I just think when something seems obvious, it maybe it isn't so obvious to others, but some of that has to do, somebody asked a question about science and things, and so I'm absolutely a strong believer. I mean, my whole life has been involved with science, and it just is a real affront to me in terms of people, you know, the last decade or so, the just denial of you know, myths and things that so
And
I think we're headed slowly in the right direction, but I sure could push them a little harder.
in this questions were what we got is of this audience, I assume, because
Okay.
I have a couple of interesting ones, and I'll start with those. How do you find good problems to work on? And I'll just add one more to that: is what does it mean to succeed in research?
Okay. Let me say, in terms of succeed in research, you know, some people would just say, you know, I mean, did you get some big prize? Did you get recognized in some way? For me, it's just much more personal. And if it gives you some psychological, you know, I solved the problem. And did it give you some psychological satisfaction that you, and, you know, maybe it turned out to be something really important. One of the example I would say is the heterojunction bipolar transistor, which I was challenged by Herb Kromer, who won the 2000 Nobel Prize and who was a real key mentor for me from the time I was a graduate student. He was a consultant when I was at Rockwell, and he said, you know, you have the materials technology, you could make one of these things. And it was something that Shockley had predicted. I just can't believe this patent. I mean, it is 40 years ahead of it where anybody even thought about such things. So I said, all right. So we succeeded, and it was, you know, a technical success. But at that time, in order to get high speed with it, you had to run it at really high currents, and it sucked power. So everybody was trying to get down to nanowatts and, you know, switching things. So it was at the borders of irrelevant. Well, in the 1990s, mobile phones came about. And so there are 2 of those heterojunction bipolar transistors in every single mobile phone today. And Rockwell turned out made quite a bit of money off of all that. They established a division, and they were one of the ones making a lot of the power amplifiers for mobile phones. So sometimes, you know, so at the time I gave a late newspaper on that at IEDM. And so it all right, I succeeded, but who cared, sort of, other than me? But it turned out ultimately to be way more important than I ever thought. So you can't always predict what's, the main thing is to choose a problem that you can solve. And
so do you want to go a little further? How do you find good problems? This is
okay. For me, yeah. For me, in a sense, it's been relatively easy because I developed, from the time I was a graduate student, I was the first one to do liquid phase epitaxy and make really high purity gallium arsenide. And so that enabled people to make gun effect devices, which were used in all the, you know, the police radars at that time, all the door openers and everything, because it was a single device and it would work at 10 gigahertz, and transistors and things were working at 100 megahertz. So it was, people were making an oscillator and then doubling and quadrupling using nonlinear elements and things to get up to gigahertz range. And these things just work straight away on transit time. And so I just always kept looking at, so that was quite successful. And then ultimately I could see, as they were starting to make lasers using liquid phase epitaxy, that it really had some limitations. And so I went back to Bell Labs, and I spent 2 days or 3 days with Al Cho, who was the father of MBE. And so most of the people at Bell Labs thought this was some waste of time out. Let Al go. This is just a waste of money. But the problems that he described to me were ones that I thought I could understand, and I had done a lot of work on the phase diagram of materials. And so I really said, all right. So there was no commercial machine. So I built the first 2 machines practically outside of Bell Labs at Rockwell. And then ultimately Varian started building those, and you could get them commercially. So it provided, and it's an incredible research tool, because you could change things. You could get almost every element in the periodic table as a highly pure material. And all the things with the hydrides and metal organic materials, it took years to purify them. And so when I was at Rockwell, I sort of really was kind of battling uphill, because the inventor of MOCVD was at Rockwell, Hal Manasevich. And so people sort of said, so why the hell do we want MBE? But I just said, you know, maybe just from my graduate school days and the fact that getting high purity gallium arsenide, doing liquid phase epitaxy, and there was so much you could do with that, I just said, I think I have a better idea how to do that with MBE. So that has been the foundation of my career since 1972. And it has been incredibly enabling, that all kinds of things I could see, people struggling with different devices, trying to do it with other materials, especially with quantum wells and quantum dots and things. And it was just, you could just go in the lab, and it was sort of a great thing. You know, sometimes students would come to me and ask about doing something. I says, don't agonize very much. Just go and do it in the lab. And if, you know, worst case, you've wasted a week or 2. you're not going to have to spend 6 months or a year trying to develop something. We have that capability right on our hands, and it's been, I would say for me, a very fortunate thing. It just is a foundation in new materials that I could, and many students, when the high temperature superconductors were first discovered, and people, I mean, it was like Neanderthals, because there were like 5 phases of the stuff. And so they would just put the stuff together in a mix, and then heat it up till it was liquid, and then quickly quench it, and it would form all kinds of polycrystalline things. They hit it with a hammer and then pick the pieces up and X-ray them and found out, all right, here's this phase. This got 2 copper oxide layers. This one's got 3. This one's got 4. And they found out, whoa, the transition temperature was going up each time. And so this student that I mentioned, Daryl Schlom, was one of the ones that he was literally had done 90% of his thesis research on gallium arsenide and aluminum gallium arsenide. But this was exciting to him. I said, well, Daryl, it's all right by me. It's going to take you a little while. He says, that's okay. My wife is graduated from law school and a lawyer, so I'm not under economic pressure. So I knew there was a machine at Varian that had been in the scrap heap for probably 5 or 6 years. It was one of their early development ones, but it was contaminated with arsenic, and so it was going to cost a lot of money to get it decontaminated and try and do. So it was just, so I just went over and asked, says, we do use this and modify it and do the high temperature superconductors. Well, so that's exactly, and so Daryl could then grow a whole, a wafer. Well, they were pretty small wafers, but one on sapphire with just one layer of copper oxide, then a layer of copper oxide with a calcium layer and a second layer of copper oxide, and then 3 intercalated layers, and then 4 and 5 and 6 and 7. And lo and behold, then you could just see the transition temperature went up like this, and at 5 it was still going up. At 6 it kind of saturated, and by 7 it was going down. And so he cascaded that in, his work on metal oxides in the high temperature superconductors really ultimately paved the way for what's happened now in all of the silicon IC stuff. So picking new problems was never very difficult for me because I had this unique materials capability. And anytime I saw something at a meeting or something that I could look at and say, hell, I can do that better. I'll just use a new material, or I can grow a quantum well or something thinner than anybody else. And so choosing material problems was pretty easy for me, I would say.
The takeaway is start with a material that has a lot of problems.
Yeah. Well, there are plenty of problems, materials with problems. And I see Subhandi and Eric nodding, and they're working on new things, power gallium nitride things, and 2-dimensional materials. So those are exciting areas.
So let me ask another one. That's a good one. So have you made mistakes in life? If so, how do you, basically the question is, I'm paraphrasing it a little bit, but what did you learn from those mistakes? Should you have avoided it?
Let me think. Yeah, I just think anybody that is not so averse to risk taking I would just say sometimes you do have a failure. One was a particularly rainy, about this time of year, and we'd had a drought, and I failed to remember my physics class, and that the coefficient of friction was a little bit less on rain-slicked leaves than it was on dry pavement, and went around a corner too fast and the wheels just went right out from under me, and I've had both hips replaced, but at that point I think I had just had one replaced, and it was only maybe like a year before, and I can remember laying there on the pavement thinking, does it still move? Am I going to have to call for take me to the hospital? I've never had that happen again. But most of the time, if you take some risks, and as I said in the things on success, the people that are really successful, you're just more adventuresome, and so some people would look at it and say, you failed. I usually describe it as a learning experience, and think what opportunity is there that I maybe don't repeat, or that it leads me in a different direction. But I can't think of really too many things I would say other than this bike wreck were truly something where I had brain failure.
By the way, if we are warmed up enough, you can ask questions directly to Jim. I mean that. Yeah, there we go. Okay. Marion, maybe Marion, try. Okay. Wow, I feel now much more scared.
I was just gonna ask you about your you commented that you see the future as like working on climate change, and I'm curious where you see promising research directions in terms of the intersection of climate change and semiconductor devices.
Oh, all right. Thank you. That's a good question. One is a lot of things I've done a lot of work on is on sensors. And so with lasers and being able to change the wavelength and things, you can do a lot of things where you can monitor all of the emissions from things, and very locally, and map them out. So I think there's a good opportunity there in making sensors and the other is one of the last things that I did was we absolutely shattered the world record for solar to hydrogen generation. And to me, that is a huge opportunity. It is absolutely technically doable. It's just to get the things, partly it's cost, and second is the lifetime of the materials. But I think that it just is going to take some research, but that solves the storage problem. It's an incredible thing. Then you can fly airplanes, you can move anything on the ground, but you can even fly airplanes. The energy density is high enough that you can. And what's the effluent? It's water. And we'll try to fly a lot more planes over California, see if we can't get more rain. But to me, that is an area that is really hopeful. And with a colleague, Tom Harmelio, and his students in chemical engineering, and my student using triple junction solar cells, the previous record was 22%, and usually if you improved it by 0.5% or 1%, it was a paper in Nature or something. We went from 22% to 33%. So it really makes it feasible if you can get in that efficiency range. So those are a couple of things, and I mean there are plenty more of just how to just get everybody to believe in light emitting diodes, for instance, in lighting.
Thank you, Jim. It seems like you opened the door for more political questions, so I will save the skiing to last. But you said you were in half a dozen or 2 dozen protests last year. So you must have been thinking about this. How can we, as an institution of education, deal with all the misinformation that's out there? It seems like I came here 35 years ago, and it's just getting worse, right? Are we completely falling down on that task of educating people? Because certainly the populace is not more educated. They're full of, misinformation, put it nicely. How do we deal with that?
Yeah, that's a, I have to say that, that early on I was, you could say I was in the other camp, but that was largely before the vaccine, when it was just being developed. And so I was very worried that there was so much political dabbling in NIH and things. I had zero confidence in how safe this was going to be. But I listened to a panel at a big medical conference, and they had the CTO of Moderna and of Pfizer. And they described in great detail the techniques that were used, some using fluorescence and being able to tag things, exactly the things I'd been working on the last 10 years, and how they could do that in 1 year, because before that, much of the testing was done on animals. And so, with a mouse or a rat, it could take 4 or 5 weeks till you could. So after that, I said, I'm number one, and I got vaccinated. And so as a result of that, understanding that, but I could kind of, in my case, it was just concerned that the whole thing had been politically jammed, that it wasn't scientific, but they convinced me that it was. So I worked for a couple of months answering questions for people that would call into the Union of Concerned Scientists, which I've been a member of for about 40 years. And so I've been kind of politically active from my days as a student when I was protesting the Vietnam War. So, I am incredibly frustrated by all that, and how to get people to believe in science. So there's a few people that, do have legitimate concerns. And, I found that when answering questions for the UCS, but there are not very many people that are searching. There's so many, it's so polarized. And if any of you are interested, you could look up a thing that was all over the news about a month ago in the town where I grew up, Newburgh, Oregon. And it is, when I was growing up, I was in the minority. I was kind of not part of the real conservative, highly religious group that didn't believe in dancing or going to movies or things. And so I sometimes say, well, what I learned, what I would hear, I just applied a negative sign to it and went in the opposite direction. So you could kind of wonder, how did this guy that's pretty politically liberal come out of such a an environment? But anyway, it's I find it extremely frustrating. So there were a couple more questions that people sent in.
Because you brought up something about growing up. So I think this is a pretty long question, so bear with me, but I want to do justice to this whole question, so I'll read it out entirely. This is from an undergrad student. As a 34-year-old former Green Beret from a town in Texas, very comparable to your hometown in Oregon, I am what may refer to as a very non-traditional student. 2 years ago, I did an independent study project that examined life at schools like Stanford for students veterans and ROTC cadets and looked for ways Stanford could improve its treatment of its very small military affiliated community to a level that is on par with other student groups. During this project, I learned that up until the Vietnam War, Stanford had an extremely robust ROTC program with hundreds of cadets versus 4 at the time of my study by the student who's asking this question. Your time as a student coincided perfectly with this dramatic shift in the culture at Stanford. Can you speak to your recollections on this change? So that's the question, and I would probably add, like, I think we can address anything that is non-traditional to this. This is definitely speaking of one particular section, but maybe your view on how do we assimilate non-traditional group in Stanford undergrad and grad, and your view on that.
Okay, so I was an active Vietnam War protester, and it certainly had nothing to do with the military. I had 2 of my undergraduate friends were in ROTC and killed in Vietnam. I just felt it was a stupid or immoral war. And I felt like that for Afghanistan and others. Certainly World War II and things. My uncle was in the Air Force for 25 years and certainly a real member of our entire family. So I just think, and I'm an active supporter of Vote Vets, who are veterans who similarly think the government use of the military is not where it should be. The military is getting used in ways that it shouldn't. And I certainly, so I think here what happened was because of the Vietnam War protests, and I only went to maybe 3, I think. And the third one was led by Bruce Franklin, who was a faculty member and subsequently was, I think, only one of 1 or 2 faculty members dismissed from Stanford because he was advocating real destruction of property and violence. And so that was beyond anything I thought. I was happy with making your feelings known, but I didn't, I was strongly against anything beyond that. And so then I didn't do any more protests after that. But what happened is that really did get out of hand. There were, I mean, buildings all over boarded up with, windows all boarded up like in the McCullough building and different buildings that students threw bricks and things through them. And campus was wild. And I think, I don't remember exactly when, but the ROTC building was down, kind of down where the tennis courts and things are now. It was burned down. So I think it's just never recovered from that. And I would just say that I think it could be supported okay. I just think the climate for the students that come here today are not particularly inclined, even some that come from military families. My cousin went to school here, and his father was the Air Force captain. And I think if you had a group, I just think that there's just not enough numbers. I don't think that they could be treated equally. I don't think they're looked down. I certainly never looked down on anybody that was in the military. My objection was what the government was doing with that, not with the people that were being brutalized over stupidity in the leadership of the country. But that it was just my personal feeling. But I think the ROTC could be built up, and maybe the route to do that is to collaborate with or work together with a school like Santa Clara or San Jose State, where maybe they do have a larger ROTC program. And if it was built up to where you had a dozen or 15 students here, where you could have actually a class of some reasonable size, and you could have somebody that could teach, a couple of courses in military strategies and things like that, and also the history of that otherwise students wouldn't see. So I don't think that there's my sense, I could be wrong, but that would be my sense.
Other questions from the audience here? Use this one so that does zoom listen.
You have told about the importance of always learning new things. Since you retired, have you learned anything new?
Well, I certainly learned a lot more than I knew about viruses and vaccines, and exactly how they're made, why it could happen much, that instead of taking 10 years to do. And one of the examples these guys cited was in developing the Salk vaccine and polio, which was an incredible threat when I was growing up. And he said, unfortunately, in terms of people getting ill, but in terms of developing the vaccine fast, we had enough data in 3 months of all the trials compared to 5 years with polio. So I guess that's the other is I've just been with all my cycling, I started listening to audiobooks. And so some of that has been a combination of political things about the last days of the previous administration, but also the brain machine, which almost everybody I've talked to that is even in the computer science world has literally never heard of this guy, J.C.R. Licklider, who, while you can't say he invented anything particular, people have described him as the Johnny Appleseed of computers. And he picked out incredibly smart people, among them Vint Cerf, who was an undergraduate with my wife here in math, and Bob Kahn, and Bob Metcalf, and others that really have been key to developing. And when he was at DARPA, and Doug Engelbart, who was at SRI when my wife was working there while I was a graduate student, he picked out some just incredibly smart people. And so you can't say he made a particular invention by himself, but he picked out an army of incredibly smart people that he mentored, funded from ARPA. He, at that time, computer was a forbidden word in ARPA. So it was called the Information Processing Office. So, and it's kind of interesting that the guy, I've forgot, Ken Burns, maybe, that founded DEC, and their first computer they labeled as a PDP, which was Programmable Data Processor, because if he was going to get any money from ARPA, he couldn't call it a computer. So he managed to find ways around things, and they were responsible for developing all of the first time sharing stuff, because everybody said, machine efficiency is important, just batch processing. I can tell you how many decks of cards I had when I was a graduate student and things. to program a computer, and you had to wait 12 hours or something to get your results and find out, oh, damn, I left a comma out of that thing. And you would change one card and reinsert your program, and it worked. So those are, I still feel like I'm learning some things, and I'm a lot bolder in telling people, you know, you should do this. my time to keep working at is my horizon has got shorter than working with all my students previously, that when they could make things happen, it could be 20 years out. But I still do love working. And so if any of you need a chair for your orals a few years down the road, if I'm still doing okay, I chaired 9 PhD orals on Zoom this past 18 months or so. And I still do really enjoy working with young people and your enthusiasm. So.
Any other questions for Jim? We're almost going to close this in maybe a couple of more minutes. So, oh, there you go.
Thank you. So my question for you is, while doing research, you said it wasn't difficult for you to find new things to research on, but has there ever been a situation where you found something new to research on, and while you wanted it to work out, it didn't work out, and how did you navigate that?
You know, I would say for me, it was much closer to just seeing that I think this is the end of the road where, you know, that I had made some good contributions. But I would just say an example of the last 10 years that I worked at a great deal with people in the medical school, because I just sort of felt like lasers, and I mean, we had been so focused on the internet and data centers and making really cheap lasers that could, you know, vertical cavity surface emitting lasers and everything that could work in data centers. And, you know, the laser cost 50 cents instead of $5,000. And so it turned out that, you know, in the near infrared where we were working on communication laser, your body is pretty transparent. You can see this if you just go put yourself in a dark closet for a little while, and then put you could take a red LED, but even just a flashlight, and you can see your bones, because in the just kind of at the red section of the spectrum where your eye is still sensitive, unless you're red colorblind. So some men can't see it, but it turns out that the absorption coefficient is about 1/10 of an inverse centimeter. So you can tag things with a fluorescent that's working in that near infrared. You can go 5-6 centimeters into the body. So I just decided that was one of those things where I had the materials technology, I could make that. So to start with, we made a little complete fluorimeter. It had a laser and a filter and a detector and an amplifier, all on a thing that was about 1/4 the size of my little fingernail. And so we could implant that into mice. So then we could look at the development of cancer, and after they then, and I remember my student that did this and worked with people in the medical school and implanted this in the little mouse, and the mouse was, so after a week, they were going to terminate the experiment. And he says, oh, I'm still getting a lot of good data. So they let it run for another week, and it didn't seem the little mouse cared. But anyway, he came into my office and says, they just terminated my collaborator for all my thesis. So I think if I were 30 years old now, or 25 or something, I think, you know, it depends on what your background is. So mine is strongly in photonics and things like that. And so that's what I found I could do with people in the medical school. They had no capability to even imagine quite, but fortunately, one of my main collaborators did have a bachelor's degree in physics. Unfortunately, he passed away a year ago at age 55. Really sad. But he had a bachelor's degree in physics, so I could kind of describe something to him, and he could almost instantly say, oh, if you could do that, we could do this. And so we worked together making all these implanted sensors and things using lasers and detectors and things. And by changing the wavelength and using different fluorophores and things, we could tag and look at different organs and things. And so my thought would be, if I were starting new, I would really focus on using that, because we did do one experiment with a guy up at UCSF with a cat, and they were putting electrodes in and then opening the cat's skull up and then imaging. And so the first thing we did was to try to image externally through the skull and see what you could see. And the key thing was, could you see enough that you could look at how that developed? Because my son went to veterinary school and then did a PhD in pathology. And once he said, Dad, you make all these little widgets. Can you do something? Because he said, you know, the mouse I found most interesting, I found it most interesting under the microscope. He says, I would love to be able to see what happened to that mouse a week from now, 2 weeks from now, a month from now. He says, I got 300 more mice and I'll see a different one each time. So that's how I kind of got started looking at this idea of real-time measurements. And I think, to me, disease kind of now is, I think we're on a good track to figure that out. But the brain is huge. And if we can figure out some way to be able to track things externally that you could look at with wearable things, not just, you know, sticking in an MRI, you have to lay real still for 30 minutes. So that's kind of good for a once a year experiment to see maybe how things are changing. But if we could do something that, and, you know, I think I would feel like by my choice of materials and able to pick regions where you could see things or tag things, you know, that you could get some of the molecules are small enough, they'll go through the blood-brain barrier. And so you could look at some things in the brain. And I think if I was 25 years old and knowing what I know now about in my skill set of being able to grow the things that I could, took me more than a few years to develop all that, but that's the kind of area to me. And the same with the environment, and being able to really understand what's happening and be able to map this stuff out now. I mean, because you can send up these little tiny satellites and things, and they're so cheap that you can, you know, put quite a few of them up there and really understand how, to me at least, how serious this stuff is.
Thank you so much, Jim. I think we covered a whole 1 hour or a little more. So this more there are defense or calls. So
yeah. So I would just say the last thing is, you know, one of the questions was, what are you most proud of? And I would say, you know, all of my graduate students, but also what I've been able to do for women. You know, every once in a while, you're just, an accident happened. You know, I got picked as the vice chair of Section 7 in the National Academy. And so I was able to appoint, unfortunately, former colleague from Stanford. She's now the Dean of Engineering at Princeton. I would love if Andrea was still here. But anyway, I got her appointed to the peer review committee, and then ultimately there was only one woman, and I said, I'm going to give you 3 more women to join you. And so then there are 4 women, and she was the chair. And so I have hopefully passed that legacy on. I managed to get Bert Giroux as the vice chair this year. So he'll be the vice chair this year and next year. So, and then the chair 2 years after, and he's done a lot in working to promote women in the EE department here. And so, you know, I'm really certainly proud of all the things that I personally have accomplished and things, but that to me is something that may have a much, much longer lasting legacy than, you know, some of the discoveries you get, and they're, you know, maybe important for 20 years, but maybe this is a more fundamental change that'll last and provide leadership. And my wife has taught me a lot. And just, you know, women approach problems differently than men do. And when you just get totally unbalanced, it's just, you get steered in the wrong direction sometimes. And so you need balance. And so I would say of the things that I'm at this stage in my life really proud of is having done that and made something that I think will hopefully be lasting. So thank you very much.
We saved the best for the last. So thank you. Thank you so much, Jim. And we greatly appreciate this opportunity.
Maybe I should say also that one of my best feats too was convincing Srabanti to leave the University of California at Davis in a tenured position to come to Stanford to an untenured position, but guaranteeing her, you know, I'll be dead if you don't get tenure. So she fortunately believed me and came, and she's doing a super job. So it's an honor to see somebody succeeding in, you know, she's inherited my MBE machine, see somebody that's doing newer kind of things that follow on what I started.
Role that we play in our lives, Eric and I both make a difference in our life. He chose Stanford as a grad student. He convinced me to join here as a faculty, so we are very thankful and proud of you. On that note, let's give another round of applause and thank you so much.
Oh, thank you. It's my privilege.